Hi everyone, and welcome to my talk on calculating drift very quickly with a library I wrote called Goko. My name is Sven Cattell. I'm a senior data scientist at Elastic, but previously, before I joined Endgame, which then got acquired by Elastic, I was a mathematician at Johns Hopkins, and I did a postdoc with Mara Majoni, who pioneered some of the work, and I've just extended that with this talk. So let's get started. So the key takeaway for this talk is basically I have built an incredibly fast drift calculator, and due to the speed, it's orders of magnitude faster than other drift calculators out there. It can be used for things other that are not traditionally considered drift. So this one is log n time to calculate the drift for a single sample, and like other ones like Wasserstein take n to the fourth time and need a large number of samples. So because it can be done in an online way and it is log n time, you can use it to defend your models, to look for like hyperlocal drift in user interactions with your model and your data set. So first things first, we're going to talk about the objective, why we care about drift. Then we're going to talk about like how this thing works, because the mathematical technique used is quite interesting and very simple once you think about it in the right way. And then results, we're going to talk about a Gaussian drift. This is like the unit test for any drift calculators that people produce, and then how drift applies to attacks. And then finally, I'll talk about the next steps. So the objective, why do we care about dataset drift? So for us, our data drifts. There's new families of malware coming out every day. There's new pieces of spam coming out every day. There's new benign software coming out every day. And also, like when people interact using email, that changes every day. So our landscape that our machine learning models learn from is changing underneath them all the time. And the traditional way of solving this is you retrain. So when your machine learning model is expecting data about here, and then the next day it's a little bit different, and the next day it's a little bit different, eventually it's not going to be able to predict things that well. It won't generalize. A machine learning model trained on data that you gathered in March may not generalize to data that you gather in August. So because we don't get this nice generalization over time because of our data set, the underlying distribution of malware and spam and whatever we deal with in the security space changes so rapidly. One of the techniques people do is like, okay, cool, I don't care about the exact pattern of my data. I care about when my models start doing badly. And so you build a dashboard that says, when I start, I'm going to track the number of errors my model makes per day, and when it exceeds a certain value, I'm going to retrain and redeploy. Or you go, well, I'm just going to retrain and redeploy this once a month or once a week, depending on your budget. But that can cost a lot of money, and it doesn't really tell you why your model degraded. And also, for us, labels are some of the hardest things to come across. Labeling a piece of software as benign or malicious concretely without using your own model to do it, which is sort of like eating yourself. Using your model to label your data that's going into your model is just a really bad idea. So to avoid that, you really should have a reverse engineer, and reverse engineers are expensive. So how confident are you in the labels you're getting? That's really hard to get right, just look like labels. So like that dashboard idea, I don't trust any of those dashboards. It doesn't work in real life. And then additionally, because we're doing machine learning, there's a whole bunch of additional attacks that affect just machine learning. Someone could be trying to poison us. Someone could be trying to sample our decision boundary where the malicious and benign exactly is decided, and then just bypass it just a little bit over. And our users, like for spam, like people have been like trying over and over and over again to see if they can modify the message or modify the message delivery system just enough that they can bypass a spam detector on Quora and Facebook and other, and like Gmail, all that stuff. So we, like our models themselves are like, they're trying to bypass them. So all in all, this required a solution that doesn't really rely on the model, and it doesn't rely on anything other than just like a good set of features, and then we can go for there. So what I've built is something that just relies on that. It's a good set of features, and we can run with it. So a trivial example of drift. So in this case, we have two distributions. We see the one on the top. Let me get a pointer. So we got one on the top is 1, 1, 2, 1, 1, and so on. And so we get 70% of our data is 1s, 20% of our data is 2s, and 10% of our data is 3s. And so we train a model and we deploy it. And this is our data from like March. And this is what we expect to see in the universe. And that could work until the end of April. And at the end of April, our data looks like this. We have 2, 2, 1, 2, and so on. So we have 30% 1s, 60% 2s, and 10% 3s. So our model was expecting the thing on the top, and it could have a very good performance on the data at the top, and very bad performance on the data on the bottom. So this is known as distribution shift. So our data, the distribution that our data is sort of generated from, like we sort of think of the malware authors and the benignware, the software developers who build benignware, as like a random process that generates data, and we ingest it, and they follow some unknown distribution that we can't see and we can't sample. But in this case, the distribution is simple enough that I can. And so this is like the distribution shift. This is what I mean by like the data moved. In this case, it moved from 1s to 2s. And I can calculate this shift. The way you do that is the Kublai-Leftwich divergence. The KL divergence between these things is calculated with this formula, where you got the 70% 1s and 30% 1s in the second distribution, and you get the first term, and the second term is built out of the 20% and 60%, and so on. And you get this 0.16. And so this is a sort of a distance calculation between these two. It's not symmetric, so it's not really a distance calculator, but it tells you like the first thing and the second thing are different. And this is really easy to calculate because I can just grab the formula here, and this is because it's discrete. I've only got 3 things that my data could be, but the problem is our data looks more like this. So our data here is continuous. We have a bunch of samples that we could have trained on in orange, and then we have a bunch of samples that came over the wire over the next month in blue. Now, I don't know, like this looks like it could be from the same distribution. Like every single time I see a blue point, there's an orange point nearby, and I can kind of like tell that this is about right. Like the center of my orange points is around here, and the center of my blue points is around here. And visually I can tell this is about right. Because I wrote the code, these are, what these are a pair of multinomial distributions, center whose mean is 0, 0, and whose covariance matrix is 1, 1 for both of them. And I've just sampled 1,000 points for orange and like 100 points for blue. And so I get this thing at the same point. But so this happens, this is like March data, and like the blue data is from April. So that's all good. But now the next month, this is what my data looks like. So my model only sees the orange data, but now I get samples that are here. You can tell that it's a little bit over, but how much of this is because I've only sampled 500 points from the training distribution, because I've only got a small number of points coming in over the wire every month compared to the number of points that I have in my training set, because we have these large industrial data sets. How much of this is because like I just have a small sampling error here versus how much is due to like an actual shift? So to me, this looks like it could be the same thing. And because I wrote the code, I know that the center for these blue points is not far off. It's just there's just a mistake with the sampling distribution, it just was shifted over more than it should have been, because we didn't sample enough blue points. But I don't get to say how many blue points I sample, because I have to live with what I get over the wire. Now here, you can definitely tell, this thing's definitely shifted over a bit, and I got some outliers. So now this is really getting bad, and my model, if I was trained on the orange points, could be, the efficacies could be really dropping right now. And if I go even further, well, there's definitely something different here. The blue points, they seem to be centered over here, and the orange points are definitely centered over here, and there's definitely a concept drift between the distributions that generated the orange points and the distribution that generated the blue points. So this is the like unit test for a thing. So can I build a system that measures that this is different from the other one? At scale, in very high dimensions, with millions of points coming into this, because it's really easy to build some systems that do this. So the tool that I reached for, and this is because the postdoc in a lab that kind of focused on this stuff, is a cover tree. So what is a cover tree? The most important part of a cover tree is it's a nice k-nearest neighbors data structure. So there's a bunch of different k-nearest neighbors data structures that you could use. You could use a KD tree, you could use a k-means tree, you could use a B tree, you can use not even a tree, you can use a locality sensitive hash. And what all these do is they sort of divide your data up. So the trees divide your data in a hierarchical manner, and it will split your data into like segments, and you only have to search for my k-nearest neighbors, the stuff that's closest to me, along certain paths of the tree. You can ignore large quantities of the data. Covertree does that by like covering your data with spheres and then like making the spheres smaller and smaller. B tree will do that with like a certain pattern. A KD tree will do that with what doesn't cover everything with spheres, but it divides things up horizontally and until it really focuses on it. But for this one, we'll describe the cover tree exactly how it works. The most important thing is this statement. It doesn't just have to do the k-nearest neighbors stuff. It can do so much more. Because it geometrically segments your data, it tells you some information about how your data is distributed in space. And we can prove, and Mara Majoni and Wenjing Lao and a few other of Nara's collaborators over the years prove that for a nice data set, a cover tree will arbitrarily well approximate the underlying distribution of the data. What nice means is we have to sample enough data from a intrinsically low-dimensional manifold in a high-dimensional space. And that assumption is called the manifold assumption, and pretty much like a lot of stuff satisfies that. There's a lot of stuff in security that doesn't satisfy that, but they seem to satisfy enough of this that the following ideas work. So let's talk about what a cover tree is. So here we're going to start with a single sphere and a single thing, and I'm going to cover my data, or pick a point at random, and I'm going to cover my data with a sphere. So yeah, it covers it well, but this doesn't segment my data, so I have to go down a level. So this would be at level 1, and I've got a radius 2 here. So if I go down to level 0, when I have radius 1, so this thing has radius 1, and that thing has radius 1, and it's segmented my data a little bit, and I have 2 children. Here, I go down another level, and I have 3 children of my parent point, of both parent points. And that's relevant. Sorry, I have 4 children of each of these parent points. So this point has these 4 children. This point has these 4 children. And so you can kind of tell that this thing is already giving you some information about my data. The number of children a point has is related to the local structure of your data. And it's really important to pay attention to the local dimensionality, and this is a very cheap way of calculating it. And if I go down further, I can get this other thing where it's starting to split up a bit more, and I can see my data has kind of matched this shape. My cover tree has matched this shape, and I've reduced the number of points I have to pay attention to, because I only have to pay attention to the centers, and I know the rest of my points are covered by that. And I've got I can go down further. I've reduced my data some more, and I've excluded some of the outliers where there's not quite enough data. So that is kind of a cover tree, and you can see that it, like, this, as you go down the tree, as you go down the levels, it kind of matches and fits with your data a lot better than at the top. So how do we get a probability distribution from the cover tree? So our cover tree will geometrically segment our data, and that geometric segmentation is relevant to the distribution, but now we've got to attach a probability distribution to that. So to me, this seems kind of, the interesting thing is, because our data is geometrically segmented and relevant, so I could either, this decision here, at this point, I could either go to the side or down. So to going to the right gives me a, it tells me that my data point is in this cluster, and going down tells me my data point is in this cluster. So that's a geometrically relevant piece of information that I get from just going with either child 1 or child 2 of my root node. For this one, I have a geometrically relevant piece of data where I'm an outlier here, and there's parts of the library that kind of help you exclude outliers. So this is an outlier because there's only one of them, but most of my points are down here. The colors that I have is the probability that I take these things. So this color here says, well, the fact that I have 2 children on my parent node tells me I have basically 2 clusters. And the colors are, well, this cluster is twice as big as that cluster. This cluster has 66% of the data, and this cluster has 33% of the data. So combining the geometric thing of going to the side and going down as whether you're in which cluster you're in, with the information about how many points are in each of the clusters, you can attach to this node a small distribution. And the distribution we attach is called Dirichlet distribution. And the Dirichlet distribution is, in Bayesian statistics, is a prior, is sort of a prior. And so now, for each of these nodes, I attach a small distribution that tells me whether I'm going left or right and what the chance, it gives me an estimate of the distribution at this point, like an estimate of like whether how many points are to the left and right. So now I have this like prior information from my training set. This is all data that I have starting off, but I know that the real distribution is probably not this, but I don't have all the malware in the universe, so I can't tell you what the real distribution of malware is. And I also know that the real distribution of malware is sort of temporal. I can only sample up to a certain point in time because I can't sample data from the future. So I can't tell you what the actual definition is because I literally can't get data from 2021. So I want to build an estimate of like what, I want to update this estimate of my distribution with stuff coming over the wire. So let me do that with 1 point. So I'm going to take 1 point over the wire, and I'm going to update this distribution with that information. So here's my 1 point, and I updated the distributions that this 1 point touched. So this point, I can take the path that this point ascends through the tree. So this point belongs to this node, and that node belongs to that one all the way up to the root, and I get a path. And for each of those elements in the path, I increment the Dirichlet distribution to inform it that I've observed a point that goes down this particular path. And when I update all those distributions, it updates all the probabilities of going this way. So now it's changed from a high probability going down, and now I've got a slightly higher, it's got slightly lower for going down and slightly higher for going to the side. Now I can go along and say, okay, well, that's one observation. Now let me see another observation. Well, here's another observation, and it updates all the things again. I update all my distributions with these this evidence that I see coming over the wire. Update again and again, and I can see that, well, my distribution has shifted. It's no longer focused on the left over here. It's now focused on the right. And this updated all my information and all my little Dirichlet categorical information, and I have a very different set of prior and posterior distributions. So here's my posterior distribution of my cover tree. Has all the information about, okay, that's a very high probability. At this point, it's a higher probability of going to the right. Sorry, going to the right, yep. My left and right's never been very good at those. So I have a higher probability of going to the right than I have of going straight down in my posterior distribution than I have in my prior distribution. So I can, and because and that's just for this node. So I have a small Dirichlet at this node, and I have the prior and posterior for the two. And now for each of these, I can calculate the KL divergence. And it's very easy for me to do that because they're all discrete. Every single distribution I need to, KL divergence I have to calculate in this case is a discrete distribution. And since my tree is geometrically motivated, all of the decisions that I made, all the probability, all these discrete probability distributions are geometrically relevant. You can tell that like this tree, I get deeper down the tree because it's denser here than here, and so this should have been denser, but I didn't collect that data from before. And I can tell that this should have been denser because now my probabilities have just flipped from this being more likely to that than that. Now I can calculate all these KL divergences and just add them up. And here's basically what the technique is. Like, you build your cover tree, geometrically relevant, calculate all your prior distributions, attach each of the prior distributions to the node. Then, as you observe data coming over the wire, you build an evidence object. So you have your prior distributions that are attached to the tree, and you have an evidence object that's off to the side. You slowly increment little counters in your evidence object. When you need to calculate the KL divergence, you combine the two, and then you can pop out a bunch of KL divergence statistics. You can sum them up to give you the total KL divergence, or you can find the maximum, the minimum, the mean, the standard deviation of all your KL divergences to give you something relevant. And you can tell me, like, give me the top 5. Give me the top 5 nodes that have a population over this with a KL divergence over that, or give me the top 5 by KL divergence of things with a population of that. And that might tell you things like, oh, this part of my data is drifting faster than this other part of my data. So this is like wonderful. I've described something that's really cheap to calculate, but it doesn't work. And here's where we come around into the thing. So here we built, say, basically the things we showed on those slides with my 2 normal distributions that I slowly spread apart. I did that in very high dimensions. I did it in 100 dimensions with 20-dimensional multinomial distribution. This is actually harder than most security data will be. So MNIST is about 10 dimensionals, and 10 dimensional. And you can ask me about why that is on Twitter if you want. And security data sort of follows this weird pattern, and this is probably harder than most security data. And what I did was took 100,000 points from one distribution. This distribution was centered at 0 in 100 dimensions and had a covariance matrix of about 1s. And I sampled 100,000 points. And I got basically a big blob of points. And then I sampled for each thing here, I sampled 500 points from a similar distribution. And then I just moved it over slightly, and slightly until I moved the things over all the way over here. It's very hard to tell the difference between 500 points and 100,000 points because this is basically covered in your original data. This is averaged over a few runs, and you can tell that there's a lot of noise here because the exact position of your nodes will basically, like, you could end up sampling a few too many points from a leaf node that spikes the KL divergence very high, or you could end up being in like big chunky nodes that have a very where when you update your prior information, your posterior one doesn't change that much, and you have a very low KL divergence. So there is a problem with this thing where it's not as reliable as the established methods, but it's so much faster. This is basically instant to calculate, and Other methods, you have to spend a lot to calculate the KL divergence, and it's honestly pointless. So to compare it to prior methods, there are a bunch of ones out there, but the one that's traditionally used, the traditional, like, can I take the divergence between 2 point clouds, is the Wasserstein metric, and it's using optimal transport. There's a whole bunch of other ones, but to me, the Wasserstein one is the one that this method compares to the best. And traditionally, it takes big O of n to the 4th. There are some modifications where you might be able to get cheaper with making some drastic assumptions in your data. But when you make those drastic assumptions, you kind of assume that you have an equal size test set and train set, and you know where the test set and where the train set goes. And that's an assumption that you can't really make in real life. So it takes big O to the 4th. My method takes log n essentially, and then k is the number of samples you want to compare it to. And the other big difference between Wasserstein and mine is mine's real time. It's online. You can calculate the KL divergence of a sequence of queries coming in real time, and you don't have to slow down a model. For the Ember malware dataset, this thing is faster than the inference time. You can get the KL divergence and then do an inference, and it basically increases the inference time by less than 10%. It can do 16,000. You can pump 16,000 samples per second through here, getting all the KL divergences you could ever need. So I said this thing. So we've shown that this thing can calculate drift, but why is this so cool? It's because we can use it now to defend our models too. It's so fast that as a user is querying me, I can pump it through this thing and calculate the KL divergence for that particular user's test set. So everybody in the world, when they're querying a model, aren't interested in everything in the universe. What we as data science do is okay, I've got my train set, my test set, I'm going to pump my entire test set through my model because I want to get the average accuracy, or I want to get the accuracy of the ROC curve or whatever you want for the test set given this model trained over that test set, that training set. But most users don't care about that. A normal user will be querying a malware model for stuff that's on his network and on his computer. But a malicious user is going to be querying a malware model for things that they have built. What they're doing is they're trying things over and over again, trying to get past our system. Versus a normal users is this is on my network, I want to know where there's good or bad, should I let it be? And then they can query it and figure it out. So they have very different patterns. The malware author might be very particular and ask the same thing over and over again, and the benign user would be spread out. So a very easy way of testing this is this thing called the test set attack, where benign user queries, and then the malicious user stops querying when they found something that is malicious, that is misclassified as benign. So they're looking specifically for a false negative, because that's a bypass in our world as people who have to maintain a machine learning model that are used for defense. That is essentially we screwed up. We used a string copy versus a string end copy. So here's the KL divergence of the two systems. So I have a baseline in green. So this is what I normally expect my KL divergence, and the big band here is the one standard deviation from the norm of my baseline. My normal users, you can see, have a KL divergence for their sequence within the one standard deviation, but all my attackers, as the moment they find an exploit, they spike up to very high KL divergence. You can see on the side that this is in log n, this is a logarithmic graph, so my attackers have literally got 100 times more higher KL divergence than my benign users. And here, what I've done is this particular thing, this uniform interest is sort of the academic perspective, where they're sampling uniformly over the entire test set. Basically, this is, I'm going to file the entire test set through my model in a random sequence in order to evaluate the efficacy. And this is what academics will do to evaluate whether a model is good or bad. But in the real world, users have interest, and this binomial interest is an attempt to retrofit users' interest onto a academic system. And you can see that when you give people like specific interests, and there's a paper and the library specifically model tells you what the interests of this binomial interest means, that the KL divergence is higher versus a baseline, but the attackers still have 10 times higher divergence than the normal users. You can also see that there are some attackers who never find an exploit. They never find a malicious piece of software that was classified as benign. And so I could build a thing that, like, okay, cool, I could do basic time series analysis to this to figure out whether I have a benign user. And if you do that, you get basically 100% accuracy for this particular attack. Carlini and Chen and Carlini have a paper where they use a different technique using k-nearest neighbors along the sequence of queries, and they get very high accuracies there, and it's up in the 98% percentile range, and this is 100%, but mostly because this is a very weird way of doing that, and that particular attack is just super easy for this model. The follow-ups for this particular work is basically I need to smooth things out. I've got to figure out ways of weighting my distributions just right, so that you don't get the noise that it currently has. And the other thing I want to do is test this on many more attacks. So there's no reason why this only works on tested attacks. It should work on basically any query-based attack, and it should be cool. Anyway, well, if you have any questions, please reach out for me on Twitter. If you want to play with the library yourself, it's open sourced on GitHub under elastic/Goko. The reason why it's called Goko is it's my what I called my grandmother, and the basis of this library, the basic concept for applying little plugins to cover trees is called geometric multi-resolution analysis, or GRMA. If you're drunk and you say GRMA a lot, it sounds like Goko, grandmother. And that's a bit too on the nose, so I'm called Goko. So I hope to see you guys on Twitter.